So on chapter 7, we did estimation, which is an aspect of inferential statistics. And the second aspect is hypothesis testing. Hypothesis testing a hypothesis is a statement made about a parameter. Remember that a parameter is a measure from the population, and a sample is a measure from, a statistic is a measure from a sample. So we usually use statistics as point estimate for parameters. When a statement is made about a parameter, we can test the validity of that statement using hypothesis testing. That is, finding a sample from which the statistic is going to tell us if the statement about the parameter is valid or not. So examples of statement could be like, is the earth warming up? What is a new medication? Does a new medication lower blood pressure? Those are several questions that people ask, and they have parameters by which they might want to use a statistic to decide if the statement about the parameter is true or not. There are generally three methods of statistical testing. The traditional method, which uses the critical value, on which we are going to emphasize more in this class, and then the p-value method and the confidence interval method. I am going to be mentioning those two methods as we move on. So the null hypothesis is one of the hypotheses involved in hypothesis testing. It is the hypothesis that states that the parameter has not changed. This issue of change is expressed by equality, in the sense that if you say that a parameter is equal to, less than or equal to, or greater than or equal to, sometimes expressions such that the parameter is at least, the parameter is at most, are used to mean the null hypothesis. The alternative or alternate hypothesis is generally the opposite of the null hypothesis. In statistical testing, we use the statistic corresponding to the parameter to make a decision about the null hypothesis. So when a researcher conducts a study, he or she is generally looking for evidence to support a claim. So a claim can be stated as either the null hypothesis or the alternative hypothesis. However, the statistical evidence can only support the claim if it is the alternative hypothesis. The statistical evidence can be used to reject the claim if it is the null hypothesis. So these facts are very important when you are stating the conclusion in a statistical study. So essentially what we are saying is that when the claim is the null hypothesis, our conclusion will be about rejecting or not rejecting it. When the claim is the alternative hypothesis, our conclusion will be to support or not to support it. But we will also get to the step of decision. The decision is always made about the null hypothesis, either to reject the null hypothesis or not to reject it. But the conclusion is about the claim. Based on the decision, we may decide either to support or not to support the claim, if it is the alternative hypothesis, to reject or not to reject the claim, if it is the null hypothesis. As we go on, we are going to do examples that will help you understand better. So let's look at this example. A medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patient who takes the medication. Will the pulse rate increase, decrease, or remain unchanged after the patient takes the medication? So the researcher knows that the mean pulse rate for the population under study is 82 beats per minute. So in the statement of the problem, we wanted to know if the medication will change the pulse rate. So the claim is the pulse rate has changed. So this kind of statement is the alternative hypothesis because it is different. It is not equal to. And we will call it a two-tailed test. It is two-tailed because it could change because it is lower. It could change because it is higher. In situation 2, a chemist invents an additive to increase the life of an automobile battery. The mean lifetime of the automobile battery without the additive is 36 months. The claim now will be the mean lifetime of the automobile battery will increase. Because it is increased that is strictly greater than, it will be the alternative hypothesis again. And this is a right-tail test. We decide whether it's right or left based on H1. So when it is greater than, it's a right-tail test. Example C, a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, a hypothesis about heating costs with the use of the insulation will be the heating bills is lowered, which is a left-tail test. So the null hypothesis is always expressed as equality. So in hypothesis testing, we assume that the null hypothesis is true, and we make a decision based on the statistic that we get from the sample. Let me show this on the whiteboard. Suppose we are making a decision about the mean. We assume that the mean is K. So the null hypothesis always assumes that the mean is K. For a left-tail test, we are assuming that mu is less than K. The opposite of mu is less than K is mu is greater than or equal to K. So if we take our sample and the mean is to the right of K, then it is consistent with the null hypothesis, which is that the mean is greater than or equal to K. Even though we write it equal to K, we understand from the alternative hypothesis that we mean mu is greater than or equal to K. So if the mean, sample mean is to the right side of K, anywhere here, we will say that it is consistent, so we do not reject the null hypothesis. If the sample mean is to the left side of K, normally we could say we are rejecting the null hypothesis, but because it was not the population mean, it was the sample mean, we will consider it as probably a sample error. But we are going to set a boundary here. And this value A, which we are going to find its standard value, this value A will be the limit from which we are no more going to feel like it is consistent because it is too much way to the left. So this area is generally called the rejection region. So if the mean was not equal to K or was greater than K, if the mean was supposed to be greater than or equal to K, we will accept that if it is to the left of K, if the standard, if this sample value is to the left, we might think that it is just due to the fact that it is from a sample. But when it crosses this point that we call the critical value, we no more agree with the null hypothesis and we reject it. Same thing would happen if it was a right-tail test. For a right-tail test, the statement is mu equals to k, and the alternative is mu is greater than k. So when we are saying that mu is greater than k, we are testing the null hypothesis, which means it is not greater than k. That means it's less than or equals to k. So if the sample value is to the left of k, it is okay. If it is to the right, it could be okay due to the fact that it is a sample, not the parameter itself. But we are going to set a value here, which we will call b, from which we are no more going to be thinking that even though it is less than k, it is due to the fact that it is sampled. We will feel like it is the critical value. So we can call it critical region or rejection region. So this is a rejection region. So the decision is based on the test statistic, which is in this case the sample mean. In order to make this comparison, we are going to find the test value, which is the sample mean minus the hypothesized mean divided by sigma over square root of n if sigma is none. And then we are going to use the level of significance alpha to determine the area to the left of alpha for a left tilt, then the z value so that the area to the left is alpha, the z value so that the area to the right is alpha. This is just like what we did for confidence interval. In case of confidence interval, it's compared to a two-tail test. So we will have minus z alpha over 2 here for a two-tail test and z alpha over 2. For a two-tail test, we will say that we assume that mu equals to k. It could be below, it could be above, but if it exceeds any of these two values that we call critical values, then we will say that it is in the rejection region. If you have a question, you can always stop me.
It's all making sense.
Okay. So there are generally two types of errors in hypothesis testing. We will assume H0 is true, and we may either reject it or not reject it. So if H0 is true and we reject it, it is a type 1 error. Like in a court case, we will assume that an individual is innocent. And if the individual is convicted, though he is innocent, it's a type 1 error. If H0 is true and we do not reject H0, is a correct decision. If H0 is false and we reject H0, it's a correct decision. If H0 is false and we do not reject H0, is a type 2 error. Just like a person is not innocent and you do not convict the person, it is a type 2 error. So type 1 and type 2 error are kind of two balanced type of error. If you are trying, if a juror is trying not to condemn an innocent person, they will likely send away a guilty person. You see what I'm saying here? In an effort to avoid a type 1 error, you will likely increase the type 2. In an effort to reduce the type 2, you will be increasing the type 1. So in this class, we are only going to focus on type 1 error. The probability of committing a type 1 error is the level of significance, which we call alpha. So alpha, the level of significance, is the probability of committing a type 1 error. It is generally given at the beginning of the problem. And the probability of committing a type 2 error is beta. So generally, the level of significance is 0.1, 0.05, and 0.01. Sometimes people could use 0.02, but most of the time that is what we have.
Is there a reason for that, by the way, those preset numbers, 0.01, 0.05, and 10?
It's just like if somebody is giving you, first of all, it is very small because it's a possibility of getting wrong. Like we are testing, there is a vaccine out there. What is the chances that somebody could be hurt by it? We don't want it large. So if the information we have is not true, we don't want it to be more than 0.1. But the reason why these numbers are commonly used is because people just want to kind of be conventional so that, for example, in medicine, most of the time they use 0.05. In some other area, they want it to be 0.01. But it is not like it has to be like that. But for our class, and most of the time, even in research, people have those values. The
Okay.
idea behind it is that it should be small. It's a small percentage of chances of getting wrong. When you get your test from the hospital, for example, and they say that you are positive, what are the chances that that result is wrong? You don't want it to be 80%. You would rather want it to be 1% or 5%. So I explained to you the critical region and the critical values. As we go on some example, we are going to come back to it. For example, if for alpha equal to 0.01, let's find the critical region for a one-tailed test. Suppose it is a left-tailed test, and we want to determine the value of z here, which is minus zc, and this area is 0.01. Then we will go to the table and look for this area. In chapter 7, you were finding this value by subtracting c from 1 and divide it by 2 and go and rate. So what is the z value so that the area to the left of z is 0.01? Then we get this number. We are going to go back to the PowerPoint to see that it's negative 2.33. So if it was for a right tail, we want to know this value. Can you tell me what this value should be if this area is 0.01?
It would just be the inverse, right?
It's not it's the opposite, yeah, 2.33. So this alpha of 0.1 and 0. Is can be compared to a confidence level of 98% confidence level, and you have shared it to both sides. If you were thinking about it only on a one side, you just look for the area, the z value, so that the area to the left is 0.01. If it's for a right tail test, you just take the opposite. So this is how you read the table. You look for 0.01 for a right tail test. You subtract it from 1. You subtract it from 1 and you get 0.099. And you look at the probability in this area that corresponds to 0.99 because it's a right tail test. As a student, what I will do is just to know that if I look for 0.01 on the table, because it's right, I will get a negative number. I will take the opposite as you did. But if you like, you subtract it from 1 and you get, this is the closest value to 0.99, and the z value corresponding to it is 2.33. Same thing for the left as we did. For a two-tail test, we have to divide alpha by 2. That is the idea of that alpha over 2 that we were seeing in confidence level. So we will divide it by 2. As we divide it by 2, you have the area between minus z and z is 0.99. This is what I explained to you by email. So the left tail is 0.05, the right tail is 0.05. The method the book is using to explain to you is always sending everything to the left. So for this side, we read the table and get negative 0.258. From this side, we subtract it from 1 before reading the table to get 0.995. 0.495 is just from 0, but if it is the left tail, everything to the left is 0.995. You read that and you get 2.58. So you can find a critical value by, if it is a two-tail test, divide alpha by 2, find the z value so that the area to the left is alpha over 2, and then you take both the negative and the positive number as the critical values. If it's a left or right tail test, just find the z value so that the area to the left is alpha. And then if it is a right tail test, take the opposite of it. If it is a left tail test, it's negative, take it as it is. So this is an example, and we have already done some of it. I want us to go to hypothesis testing per se. You can always go through it from the PowerPoint in the book. So in hypothesis testing, we have 5 steps. The first step is to state the hypothesis and identify the claim. So generally, the claim is made in the problem that you have. You have to look carefully if the statement about the parameter involves equality, that is greater than or equal to, less than or equal to, or equal to. If a statement is like that, then that claim is in the null hypothesis. And you will write it as equality for the purpose of the work. Then find the critical values. Using alpha, you determine the critical values. Then compute the test value. We are going to have two methods. When sigma is known, we use the z-test. When sigma is unknown, we use the t-test. You make the decision now based on whether or not the test value is in the critical region. If it is in the critical region, you reject H0. If it is not in the critical region, you do not reject H0. Based on the decision that you take at this level, you now go back to see if that decision, if the claim is H0, your conclusion will be either to reject or not to reject H0. If your claim was H1, that is the alternative hypothesis, your conclusion will be either to support or not to support the claim. So we can also use the TI-8384 calculator for those who have it. It makes things much easier, but I don't always assume that you will have it. So that is why if you were to have the calculator, then we will use the P method the P-value method that I will explain later. It is when you are using calculator that P-value method becomes easier. So we use the z-test if the population is normally distributed or the sample size is large enough and sigma is none. The test value is expressed here as the sample mean minus the mean, population mean, divided by sigma over square root of n. Example. A researcher reports that the average salary of assistant professor is more than 42,000. A sample of 30 assistant professors has a mean salary of 43,260. At alpha equal to 0.05, test the claim that the assistant professor earn more than 42,000 per year. The standard deviation of the population is 52,000. So first we identify the claim. It is clearly stated here that the claim is the assistant professors earn more than 42,000. Because equality is not into this expression, it will be the alternative hypothesis, and the null hypothesis will be mu equal to 42,000. So alpha equal to 0.05 is a right tail test. We can look for the critical value. So the critical value here will be, I want to explain that here. Is a right tail test. Alpha is 0.05. So we are going to look into the Z distribution table for the area, the Z value, so that the area to the left is 0.05, or the area to the left is 0.95. That is doing 1 minus 0.05. If you look there, as we did in chapter 7, when we were doing 90% confidence level, when we divide 10 by 2, we had 5%, 5%, that was 0.5. You will get 1.65 here. So that is the critical value. Now we find the test value by applying this formula. The sample mean was 43,260. The hypothesized mean was 42,000. The population standard deviation, 5,230 divided by square root of 30, and we will get 1.32. So with this test value of 1.32, we now, that is the third step. First step, state the hypothesis. Hypothesis where H0 mu equals to 42,000. H1 mu is greater than 43,260. And then the test, the critical value is here. The test value we say was 1. So we now check, is this critical value in the rejection region or not? What do you think? Is it in the rejection region or not?
It's not.
It's not. It's not on the rejection region. So we do not reject H0. Let's go back to PowerPoint. So we do not reject H0. If we do not reject H0, and it was not the claim, there is not enough evidence to support the claim that assistant professor earned more than 42,000. So we know we cannot reject H0 based on our statistic, that is the test value or test statistic. Let's look at this example. A researcher claims that the average cost of men's athletic shoe is less than $80. He selects a random of 36 pairs of shoes from a catalog and find the following cost. Is there enough evidence to support the researcher's claim at alpha equals to 0.1? So the claim here is the average cost is less than $80. So we can enter those values into Excel. We are not going to, you can always do that from what we learned in chapter, what we learned in. Do you have a way to do those type of computation?
Yeah, with those lists, I have a TI-83.
Or if you have a TI-83, you enter into it, and then you can even get the test value from your calculator. So you use any method for those who don't have a TI-83, 84. You use any method. If you are given data value, you use any method like Excel or your calculator to find the mean and the standard deviation. But when you have so many values, you can't do this manually. You need to learn how to use Excel. You enter the values into Excel. And if you forget, go to chapter 3 and you will learn that. I'm speaking for those who are listening to us from the recording. So, do you have your TI-83 calculator with you now?
Yes, I do.
Okay. So we are not going to, you know how to enter values into a calculator, right?
Yeah, put the list in. I know how to do the Z-test as
okay. Well. Okay, good, good. So now we want to find a critical value. With alpha equal to 0.1, if you read the Z table, the Z value so that the area to the left is 0.1 is negative 1.28. And now using the sample mean of 75, if you compute the sample mean of the data, the hypothesized mean is 80. The standard deviation for the population was given as 19.2 divided by square root of 36, you get negative 1.56. Negative 1.56 is in the rejection region. So we reject the null hypothesis. We reject the null hypothesis, and the claim was not the null hypothesis, so we can support the claim. There is enough evidence to support the claim that the average cost of men's athletic shoes is less than $80. So cost of rehabilitation. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $25,226. The standard deviation of the population is 3,251. At alpha equal to 0.01, can it be concluded that the average cost of stroke rehabilitation at the particular hospital is different from 24,670? So if you have a TI-83, you can enter this and then use the Z-test because sigma is none. Otherwise, you will have to use a calculator. We state the hypothesis. The claim here is mu is different from 24,672. With alpha equal to 0.01, we will divide it by 2 to find the critical value to be 2.58 plus or minus 2.58. That is 0.05 to the left, 0.005 to the right. So now we compute the test value and it is 1.01. 1.01 is not in the rejection region. So there is not enough evidence to support the claim that the average cost of rehabilitation at the particular hospital is different from 24,672. So the idea of the p-value method is that we want to, the idea of the p-value method is that we have the critical value, which is 1.32. Then the p-value is the area to the right of the test value for a right tail test, the area to the left of the test value for a left tail test. So we find that area. If it is bigger than alpha, then it takes us out of the critical region. If it is less than alpha, it is within the critical region. So when we are using the p-value method, we make decision based on whether the p-value is less than or greater than the alpha. So if you are using your TI-83, 84 calculator, in addition to the test value, you will see the p-value.
For those yes. Two-tailed tests, when you're comparing the p-value with the alpha, are you comparing the p-value with the alpha times or divided by 2, or?
No, if you have the p-value like from your calculator, then it is the p-value.
Yeah.
Let me explain what actually happened. If you had a two-tail test, right? If you have a two-tail test, for example, if alpha is 0.05, then you will have so if you have a two-tail test, then on this side, On this side, we will have 0.025, and on this side, 0.0. So alpha is now 2 times the area to the tail. So now if you have your test value here, and you find this tail, you want to compare it to alpha over 2. But if you have the p-value, you want to compare it with alpha. So the p-value will be double, is the double of the area to the left or right of the test value.
Okay, so that's what I was getting hung up on that question in the email I sent you.
Yes. So if you had taken if you are reading the table to find the p-value, then because you will find z and find the area to the left, double it and compare it to alpha. Because otherwise compare it to alpha over 2. It's a little bit confusing, but if you are using your calculator, the p-value that they give, don't change it. Compare it to alpha directly. So to find the p-value for a two-tailed test, you find the area to the left or the right of the test value and double it to get the p-value. So you don't need to do anything with the p-value, like divide it or multiply it.
Or the A either.
Yeah, the alpha. The alpha is alpha if you get the p-value, but when you are working it manually, you want to recall that if it's a one-tailed test, the p-value is the area to the left or the area to the right of the test value. If it is a two-tailed test, that area has to be multiplied by 2 before you use the general rule that compares alpha to p to make a decision.
All right, that makes sense. Yeah.
Okay, thank you. So that is it with the p-value. So let's look at this example. A researcher wishes to test the claim that the average cost of tuition and fees at a 4-year public college is greater than 5,700. She selects a random sample of 36 4-year public colleges and finds that the mean to be 5,950. The population standard deviation is 659. Is there enough evidence to support the claim at 0.05? So we will first state the hypothesis and now find the test value. And we will read the table to find the area to the right of 2.28. Because it's a one-tailed test, we find that area to be 0.0113. So we compare it to alpha. Because that area is less than alpha, we reject the null hypothesis. And then we support the claim. I don't give you money. I don't even think I have questions on p-value on the quiz, but if you happen to see one, that is how to answer. I try my best to limit most of the question to the critical value. So in section 8.3 is when sigma is unknown. If you understood what we did in 7.3, that's essentially the same thing here. If the population is normally distributed or sample size is large enough, we use the t distribution when sigma is unknown. The degree of freedom is n-1. Here, to find the critical value, you go to the t distribution. For example, find the critical value for alpha equal to 0.05 with a degree of freedom of 16 for a right-tailed test. For a right-tailed test, this is a one-tailed test, so 16 degree of freedom, the critical value is 1.746. If it was a left-tailed test, it will be minus 1.746. We can do the same thing. You can practice by checking the t value, the critical value for alpha equal to 0.01 with degree of freedom of 22 for a left-tailed test. It's essentially, I want you to practice this and to confirm that t equal to negative 2.508. For a two-tailed test, you use the degree of freedom, which is n-1, sample size -1, with and then you choose two-tail test. You see here there is one tail and two tail. So you choose two tail, and you will have both sides. For example, negative 1.734 and 1.734 for a two-tail. Whatever you read, you take both sides. Example, a medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim? Here, the claim is the average number of infections per week at the hospital is 16.3. So it's equality. So it is the null hypothesis. And then the alternative hypothesis is mu is different from 16.3. Find the critical value for alpha equals to 0.05 with a degree of freedom of 9. So we use the table, the T distribution table. You can also use your TI-83 calculator to find this, but if you have a TI-83 calculator, you can just use it for the T test. And the test value is 2.28. And the critical value, reading this from the table, you just use alpha equal to 0.05 and then read the table for two-tail with degree of freedom of 22. You will get, I'm sorry, not 22, degree of freedom of 9 because there are 10. N equals to 10, the degree of freedom is 9. You will get negative 2.262 and 2.262. Our test value was 2.46, is greater than the critical value, so it is in the rejection region. So we reject the null hypothesis, and we will say there is enough evidence to reject the claim because it was the null hypothesis, and we reject it. So there is enough evidence to reject not the null hypothesis. At the conclusion is about the claim. There is enough evidence to reject the claim that the average number of infections is 16.3.
Could you, I'm just curious, or would you be able to use the p-value still in that to be able to figure that out? Comparing
Yes.
PA? So there's more than one way.
Yeah, you can use the p-value. If you use your calculator, it will give you the p-value. But using the test, the T table is a little bit more complicated. But using the calculator, you will get the p-value. And you will see that this p-value is less than alpha, and you will reject the null hypothesis and make the same conclusion.
Okay, okay.
Mm-hmm. So this is another example, which is using the data. You can also do this. We are not going to enter the data. And if you are using your calculator, if you have a TI-83, I don't see the reason why you want to calculate the variable. So I put it there if for those who still want to manually do the work, but you rather go to test and choose option 2, T-test, and complete using data, not statistics. So I'm skipping this example because they are essentially the same. In this example, the alternative hypothesis is mu is greater than 36.7, and the test value is 2.517. So using the critical using the degree of freedom of 14, we will find the critical value to be 2.517. And the p-value is somewhere between 0.01 and 0.025. So generally, this p-value is read from that table and don't generally ask you questions about the p-value. So I will skip it, but for those who have the TI-83, you get the p-value from it. So in 8.4, the z-test for proportion is essentially the same thing. We want NP to be greater than or equal to 5 and NQ to be greater than or equal to 5. We use the Z distribution and the test value is this formula. Example, a dietitian claims that 60% of people are trying to avoid trans fat in their diet. She randomly selected 200 people and found that 128 people stated that they were trying to avoid trans fat in their diet. At alpha equal to 0.05, is there enough evidence to reject the dietitian's claim? So the claim here is that P equals to 0.6. It is the null hypothesis. So we already know that our conclusion will be about reject or not reject. With alpha equal to 0.05, we can use, because it is a two-tail test, alpha equal to 0.05, 1.96 is the critical value. The test value, we use the information from the problem to find P hat, which is 0.64. 0.64 minus 0.6 divided by the P and Q here is the P and Q, the P from the null hypothesis. Q is 1 over P. I'm sorry, 1 minus P. Q is 1 minus P. You fit it into this formula. You can do it step by step to get the test value to be 1.5, 1.15. So 1.15 is not in the critical region, so we do not reject the null hypothesis. Remember that it was the claim, so our conclusion will be there is not enough evidence to reject the claim that 60% of people are trying to avoid trans fats in their diets. So this is essentially the same type of question that we had, so I will skip it. So 8.5, chi-square test for variance. You remember the chi distribution in chapter 7? So we are going to learn how to find the critical values. The test value is n minus 1 times s squared over sigma squared. Sigma squared is what you get from the hypothesis, the null hypothesis. So to find the chi-square, to find the critical value, the degree of freedom is n minus 1. For a right-tail test, you use the degree of freedom, which is 15 and 0.05. For a left-tail test, you are going to take alpha over 2 to the left here, but the area to the right is what you will use. So you will use 0.95 if it was a left-tail test. We will do the next example. Here, find the critical chi-square value for 10 degree of freedom when alpha equal to 0.05. So this is where we have 0.05. We will do 1 minus 0.05 because the chi-square distribution is a right-tail distribution. So for a left-tail test, you will do 1 minus alpha before you read the table. And you will compare 1 minus alpha, match it with the degree of freedom of 10 to get. So we have degree of freedom of 10.95. For left tail, you do 1 minus alpha for chi-square distribution. For a two-tail, it's exactly what we did in confidence interval. You do alpha over 2 and 1 minus alpha over 2. You will find those two numbers. You will find those two numbers on the table. One will be to the left, the other one to the right. Both numbers will be used as critical values. Example, an instructor wishes to see whether the variation in scores of the 23 students in her class is less than the variance of the population. The variance of the class is 198. Is there enough evidence to support the claim that the variation of the students is less than the population variance. The population variance here is 225. At alpha equal to 0.05, test the hypothesis. So the statement is, we need to know what is the claim. The claim is the variation is less than 225. So that is the claim. So next, we find the critical value, alpha equal to 0.05. It is a left tail test. I'm sorry, it's a left tail test. So we are going to subtract it from 1 and then read the table to find the critical value to be 12.338. So now to compute the test value, we do n minus 1 times s squared over sigma squared, and we get 19.36. So it is not in the critical region. So we do not reject the null hypothesis. There is not enough evidence to support the claim that the variation in test score of the instructor student is less than the variation in score of the population. Nicotine content. A cigarette manufacturer wishes to test the claim that the variance of the nicotine content of its cigarette is 0.644. Nicotine content is measured in milligrams and assume that it is normally distributed. A sample of 20 cigarettes has a standard deviation of 1. At alpha equal to 0.05, is there enough evidence to reject the manufacturer's claim? So here the claim is the variation is equal to 0.644. It is the null hypothesis. Using the method that we had, alpha equal to 0.05 divided by 2, you get 0.025, subtracting from 1, you get 0.925. Using the degree of freedom of 19 and matching it with those two values, 0.975 and 0.025, we will get the critical values, 32.852 and 8.907. The test value is 29.5. So it is not in the rejection region. So we do not reject the null hypothesis, and we conclude that there is not enough evidence to reject the manufacturer's claim that the variation of the nicotine content of the cigarette is 0.644. So we can also test hypothesis using confidence interval. This is not, usually I don't ask you a question about that. But what that actually means is that when the null hypothesis is rejected, it is in a hypothesis situation, the confidence interval of the mean using the same level of significance will not contain the hypothesized mean. So if you compute your confidence interval and the hypothesized mean is not in that interval, you do not reject the null hypothesis. If it is in the interval, you do not reject the null hypothesis. If it is not, you reject the null hypothesis. It's as simple as that, to use a confidence interval to test hypothesis. If the null hypothesis is in the confidence interval, you do not reject it. If it is not, you reject it. Actually, the confidence interval gives us the range of values within which the parameter is. Since the null hypothesis is always the parameter equals to, if it is not in the confidence interval, we do not reject the null hypothesis. If it is not in the confidence interval, we reject the null hypothesis. So this is an example. Yep, I just try to move a little fast so that we make less than an hour. I don't know if you have any question so that I can go back to it.
I had one, but I forgot.
No, we can just quickly go back if you can see it where it is. Do you know which section it could have been?
No.
Do you know whether it was about the mean or proportion or variance? But actually, if you have a question, as usual, you can send me an email.
I think that's what we'll have to do.
Okay. Okay, have a good evening.
All right, you too. Thank you so much.
Thank you, Tana. Take care.